ME204, Particle Kinetics using Impulse, Linear Momentum, and Conservation of Linear Momentum. Well, we've talked about impulse and momentum of a particle and defined that our linear momentum is a mass times a velocity vector, and our linear impulse is a force vector times a change in time. Well, now let's put everything together, just like we did in energy. If we look at impulse and momentum for a single particle, the mass times the initial velocity vector plus the impulse vector is equal to the mass times the final velocity vector. We can solve these by looking at an initial kinetic diagram plus a free body diagram that shows what the forces are and as a result gives us the impulse, and then a final kinetic diagram. Note that in this case our kinetic diagram shows velocities rather than accelerations. So if we have a mass that's not moving initially, we don't draw any velocities on that mass. The forces that are acting on it may be a weight, a normal force, and some driving force that's applied for a certain amount of time. And then finally, we have a mass times velocity or momentum associated with that object. What would the equation look like if we had a system of particles? Well, we would sum all of the initial momentums of each particle and add that to the sum of all the impulses and set that equal to the sum of all the final momentums. So if we have a system of particles that aren't moving, we have no initial momentum associated with those particles. We may have forces acting on the particles which would cause an impulse, and the result would be that each of the particles then have momentum associated with them. Now it's important to know how to choose a system when solving these problems. Remember that only the external forces cause impulses on the system. So what if we chose a system like this for our system to solve the problem? In this case, we would have a weight for mass A, a weight for mass B, and we wouldn't need to find the tension because that's internal to the system. But we would have to find the reaction forces and show what kind of an impulse they cause. So in this case, we'd have all of the reactions across the top of this pulley system that would need to be included in the equations. Let's look at another way to choose systems for this kind of a problem. Again, remember, only the external forces cause impulses on the system. So let's carefully choose the systems that we want to use to solve this problem. What if I chose this as a system? Well, then I would have the weight of the block, and I'd have the tension T1 on the pulley as the forces acting on this system. You would have to find the unknown T1 in this case. But that only solves part of this pulley problem. Now what if I chose this as a system? Well, I'd have the weight of block B, but I'd also have another tension T2, and I would have to find the unknown T2 in order to solve this problem. Can we choose a system so that there's no net impulse? What if I've got two vehicles here, a semi-truck and a pickup truck, that are traveling towards each other and are going to run into each other, and they're not putting on their brakes at all, they're just rolling? Can I choose a system so that there's no net impulse? Well, if I select both vehicles as they collide, then I have a system with no impulse. The forces between the trucks are equal and opposite and are applied for the same amount of time, which means that the impulses negate each other or cancel each other out. So we have a system with no net impulse, and we have conservation of momentum. Conservation of momentum occurs if the impulse is zero. The initial momentum is equal to the final momentum. It may transfer from one body to another, but the momentum is the same. Here's an example. Let's find out what the velocity of block A is after it's fallen for 2 seconds from rest. The weight of block A is 15 pounds and the weight of B is 5 pounds. Let's look first at block B. There's our weight of 5 pounds and we have two tensions in the cable above block B. If we look at our momentum equation, our initial momentum plus or minus the impulse equals the final momentum. We know that it starts from rest, so our initial momentum is 0. I like to choose positive in the direction of the motion. So we're going to choose upward as positive, so we'll have our forces are 2t minus the weight, the mass of b times gravity. All of that times the change in time gives me my impulse. That impulse causes motion, or causes a change in momentum. So we have a final momentum of block B, which is the mass of B, times the velocity of B. If I plug in what I know, I'm left with two unknowns, the tension of the cable and the velocity of block B. So we have to look at another part of this problem in order to solve it. Well, let's look at block A. In this case, I've got a weight of 15 pounds and one tension in the cable. We'll use the same impulse and momentum equation. Again, our initial momentum is 0 because there's no initial velocity. And I like to choose positive in the direction of motion, which in this case, A is moving down. So my weight, the mass of A times gravity, minus the tension in the cable, T, all of that times the time gives me the impulse that causes the change in momentum. And my final momentum is the mass of A times the velocity of A. Plugging in what we know, we have, again, another equation with two unknowns, but we add an extra unknown, the velocity of A. So we need a third equation in order to solve the problem. We know that this is a 2-to-1 pulley, therefore, twice the velocity of B is equal to the velocity of A in magnitude. If we solve these three equations simultaneously, then we get that the velocity of A is 49.5 feet per second going downward. The velocity of B is 24.8 feet per second moving upward. And the tension in the cable is 3.47 pounds. We were looking for the velocity of A, and we have our answer, 49.5 feet per second. Let's look at another example that uses conservation of momentum. In this case, we have a 75,000-pound semi-truck that's traveling 10 miles per hour when it strikes an 8,000-pound pickup truck traveling at 65 miles per hour in the opposite direction. Neither vehicle applied the brakes before the collision, and the two vehicles become entangled. What's the final velocity and direction of the vehicles immediately after the collision? Well, first let's choose our system. We're going to choose both vehicles as one system. The sum of our initial momentum plus the sum of the impulses equals the sum of our final momentum. We chose our system so that the net impulse is 0, so we can eliminate that from our equation. Now we take the initial momentum of the semi-tractor trailer plus the initial momentum of the pickup truck, and that will equal the total mass of both the truck and the semi-tractor trailer, since they become entangled, times their final velocity. We can write in our equation with what we know, so that we start with the initial mass of the truck, of the semi-tractor trailer, times its speed, 10 miles per hour, with our conversion factors to get everything into feet per second, plus the mass of the pickup truck, 8,000 pounds, divided by 32.2 to give us a mass, times its initial speed, which is negative 65 miles an hour because it's in the opposite direction, times its conversion factors, give us the final mass, which are both vehicles combined, times the final velocity. Canceling out what we can, and solving for our final velocity, gives us a final velocity of 4.06 feet per second, or 2.77 miles per hour to the right. So after this collision, both vehicles will be traveling in the same direction that the semi-truck was initially traveling. Our next topic is the coefficient of restitution, line of impact, and plane of contact.